guys. Greetings to every one of you, and welcome to today's special lesson, our very first lesson on the topic physical quantities and units. So we are in physics. We are going to take you down the entire physics syllabus in our special course. Yes. So in this course, you're going to be learning everything that concerns advanced level physics, and it also goes for those who are writing competitive entrance examination into professional schools like medicine, engineering, engineering school like NAPI, Polytech, Public Works, FET, Caltech, COT, just to name a few, and many others. So if you fall within this category of people I have named, you are highly welcome to this lesson today. Also, among other things, if the exam you're going in for has not been shortlisted, and this course is required for your exam, you're also welcome. I will make things very easy for you to understand. In this lesson, I'm going to take it right from the base. I'll make sure I explain everything that you will need to know. And should in case, if you have difficulty understanding a particular part of the lesson, do well to leave a comment below so that I will review and then I'll have to explain it in the subsequent lesson. Or then, as the case may be, I may come up with a new lesson just to explain that concept very well. You can also write to us directly. If you check on the website, you're going to see contact information, our phone numbers. If you're in Cameroon, then you can contact us directly through those numbers. If you're out of Cameroon, simple, you just add the country code 237 before the number, and then you can give a call directly. You can join us on WhatsApp or any of our social media handles. So the reason for this course is because we want success at the end. We want you all to be successful in your various competitive exams that you are going in for. So first thing first, good luck to all of you going in for medicine, going in for NAPI, going in for MLS, going in for public works, going in for FET, Caltech, COT, and so on. Subtict. Good luck to all of you. I wish you understanding as we go through this lesson. I wish you proper understanding, because it is understanding that brings success. So you need to understand all I will be doing, and then in the exam you will find yourself doing what you know. Yes, and then when results are published, we should find people happy to have passed their exams. All right, so without wasting of time, we get started. The first topic, we have 30 topics to go through in this course. If we do not add, because with time we may want to split some topics, or we may want to bring some topics together for them to coalesce. Yes, but then there are 30 solid topics that have to be exhausted. So just join me through. I'll make things very easy for you to understand. So today we're looking at physical quantities and units. The first topic, the first most important topic in physics. So we will be looking at physical quantities, base physical quantities, derived physical quantities, vector quantities, scalar quantities, and SI units, and so on. So now the first question that begs for an answer is, what is a physical quantity? we are saying that we want to be talking on physical quantities and units. So it is proper to first of all discuss what physical quantities they are. What is a physical quantity? Simple. A physical quantity is any quantity that can be measured. So any measurable quantity is a physical quantity. So I asked a question some time ago in a prepare group, academics cognitive, where at the center actually, and I was asking examples of physical quantity. A human being breathing, I mean alive, said gave some examples like rice, what were some of the water, and so on. And I would like to say those are physical substances, not physical quantities. Physical quantities are those quantities we can measure. Mass. When you are measuring, people say they can measure water. When you are measuring, you are not actually measuring water. You are measuring what? The volume of water or its mass. You can measure the distance from Yaoundé to Douala. What you are measuring is not the road. What you are measuring is distance. So the physical quantity that is constituted there is distance or length. Each physical quantity has units of measurement, also has measuring instrument. So it's important to know, while we have already defined physical quantity, I would like to go ahead now and talk on two types of physical quantities. We have basic, otherwise called fundamental physical quantities. Then we have derived physical quantities. For the base physical quantities, there are 7 of them in number. It is important to know the base physical quantity, its SI units, and also its measuring instrument. So I have written them down. For base quantities, I said all base quantities, they constitute 7 of them. They have SI units, and then they have measuring instrument. We have mass. The SI unit of mass is kilogram, and then mass is measured using the balance. It can be a beam balance, a spring balance, a triple beam balance, as you people know it. It can be an electronic balance. We have length or distance. It is measured in meter, and then using a meter rule, or as the case may be, a ruler or a tape, a measuring tape. We have time. Time is measured in second using a stopwatch. We have temperature measured in Kelvin. Kelvin is the SI unit for temperature, measured using the thermometer. We have electric current, which is measured in ampere, and it is measured using the ammeter. We have amount of substance, which is measured in mole, and last we have the luminous intensity, which is measured in candela using the photometer. Now, after hearing about all this, it will interest me to inform you that when we say SI units are actually different from what we call base units. SI stands for let me use my pen. All right, I would like you to take a look at what I've written here. SI stands for Système International d'Unité, as the Frenchman puts it, and in English, the International System of Units. That's the meaning of SI. So it means that internationally, if we say, when we are talking of the measurement of mass, it is recognized internationally as mass being measured in kilograms. Yes, So now we have base quantities. We also have derived quantities. Or any quantity that's not among the one I have listed in the course of looking at base quantity, those quantities are derived. So now we will have to go ahead and talk on derived quantities. Now, the only thing I want you to know about derived quantities is that derived quantities are a combination of base quantities. Derived quantities are obtained when we put base quantities together. Yes, for example, when we take distance and we divide it by time, it should give us speed. When we take displacement and we divide it by time, it should give us velocity. When we now take that velocity and we divide it by time, it should now give us acceleration. When you take mass and you divide by volume, it should give us density. When you take force and you divide by area, it should give us pressure. When you take force and you multiply by acceleration, it should give us force. So you now see that we take base quantities, we put them together, it gives us derived quantities. And you can continue deriving more quantities from those derived quantities. So now it simply means that from one derived quantity, you can move backward. You can take, for example, from force. You know that force is mass time acceleration. Acceleration itself is derived. So acceleration now is what? Velocity over time. But now velocity also is derived, which is displacement over time. So you see that we have brought together displacement, time, and mass. And after manipulating them, they give us force. So that's the meaning of derived quantities. Excuse me. I want to believe you're understanding what I'm putting through. My objective is to school you through physics so that by the time you sit in the examination hall, you should sit in front of your paper like a king or a queen, waiting to triumph whatever question you find on the question paper. So now, like I said, all derived quantities, there's an example that we are going to look at here. I want you to take a look at this. Here, like I said, all derived quantities, they have their constitute base quantities or fundamental quantities. And now here we are taking an example of force. We know that from Newton's second law of motion, or the fundamental relation of dynamics, force is equal to mass time acceleration. But now this acceleration here alone is what? Is derived, which is velocity over time. Acceleration is v on t, right? So you can always when you look at a derived quantity, you can always take them down to their corresponding base quantities. But it is not a rule that must be followed. Remember, in the exam, you're answering questions. So as a result, you work based on the question that approaches you. Now, if you want to know the units of force, the base units, so I want you to know that for derived quantities, they have both the base units and their SI unit. For example, for force, SI unit for force is Newton. Everybody knows that. Even someone who has never done physics knows that force is measured in Newton. Now, if you want the base unit of force, you have to take the units of the corresponding base quantities. For example, here we have mass. Mass is measured in kilogram. Acceleration measured in meters per second squared. I hope you know how it comes about, because acceleration is velocity over time. Velocity is what? Displacement on time. So it simply means that acceleration is what? Displacement on t squared. So this gives us the unit of acceleration being meters per second square. And this now is the base unit for what? Force. So with this, you can also find a base unit for any other derived quantity that you may ever come across. All right. For example, we could say energy, power, impedance, or whatsoever. All right. So that said and done, we have actually successfully spoken about base and derived quantities sufficiently. Now we will have to move ahead looking at homogeneity. Yes, we will look at homogeneity. And the question that begs for an answer here is, what is homogeneity and what is a homogeneous equation? What does it mean when we say an equation is homogeneous? So that is what we must look at as a matter of urgency. All right, guys. Yes. What is a homogeneous equation? After looking at units, after looking at fundamental and derived quantities, it is of importance to discuss homogeneity, which is a phenomenon in physical quantities and physical equations. What do we use homogeneity for? What is the use of homogeneity? When we are not sure, excuse me. All right. When we are not sure whether an equation is correct or not, we can use the units of the different quantities to check whether that equation is correct or if that equation is wrong. Now, how do we know? What result do we expect when we are doing this? When the units of the quantities on both sides of the equation are the same, that equation is a homogeneous equation. I come again, when the units of the quantities on both sides of the equation are the same, we say the units of the additive terms on both sides of the equation, when they are the same, then we say the equation is homogeneous. So a homogeneous equation is one in which the units of the additive terms on both sides of the equation are the same. It is important, I must talk about this, I must mention that in physics, everybody knows that when we talk about homogeneity, an equation can be homogeneous but wrong. An equation can be homogeneous but incorrect. Homogeneity does not take into consideration unitless constants or dimensionless constants. Even though I did not add them in the notes, base physical quantities, they have dimensions. For mass, it is capital M, and we use square bracket for dimension. Always know that. For length or distance is capital L. For time is capital T, dimension. So now, for example, if we need a dimension of Acceleration. You know acceleration. Acceleration is velocity on time, right? And then velocity is what? Displacement on time. So see, it now means that acceleration is displacement on t square. What's displacement? The dimension of displacement is L. The dimension of time is t, and it is squared. So, and it is over t squared. So we have on lt to the negative 2. Yeah. So now, what if it was mass? What if it was force? You know that force is ma, right? Yeah. And this is already a here. The dimension of mass is capital M. Then acceleration lt to the negative 2. So it means the dimension of force is mlt to the power minus 2. All right. What I've just done is known as dimensional analysis. Okay. Now, an equation can be homogeneous but wrong. An equation can be homogeneous but incorrect due to unitless constants which may be present or absent in a physical equation. For example, we know that, let's talk about kinetic energy, for example, Ke. We know that Ke is half mv squared. Now, this half is unitless. This half is dimensionless. It does not have a unit. As a result, if you use dimensional analysis, we will have that Ke is equal to mv squared, and it will be dimensionally correct but physically wrong. Why? Because this one will be absent, but using dimension, this is unitless and it's not considered. I think the most important thing I was supposed to say, I have said it. So now, to find the dimension, or let's just look at an example which I've included in the notes here. At the end of the lesson, you will have this note in PDF form to go through it and then do your exercise, which I will leave here. I call it test yourself. I call it now test yourself. So by the time you go through the note now, you then test yourself. You send it to me and I'll correct it. If I don't have enough time correcting them, I'll make sure I send it to other collaborators, teachers to mark them and make correction for you. So as to make sure that the lesson is properly understood. All right. Now let's read this. The question here. When a body falls in a vacuum, all its gravitational potential energy is converted into kinetic energy. Good. So you know that gravitational potential energy is given by mgh. And when a body falls in a vacuum, all this GPE, gravitational potential energy, is converted to kinetic energy. And kinetic energy is given by half mv squared. Yes. Now, they say show that this is a possible solution to this equation. The first thing you have to do is to write down the units of the quantities on each side of the equation. You write the unit of mgh, you write the unit of half mv squared. And that's where you will find out that half now is unitless. Then you compare the two sides. When you compare the two sides, You are going to have a common unit. For example, mass is kilogram, g is acceleration due to gravity, which is meters per second, meter per second square, h is meter. So it means you have kilogram meter square per second squared. So on the left hand side of your equation, you have kilogram meter square per second square. On the right hand side, you will have the same thing. So the unit on both sides of the equation will be the same. You get a point. For example, let's just do it. We have half mv squared. Unit of half is unitless. M is kilogram. Then v squared. You know that v, the unit of v, which is velocity, is meters per second. So when you now square this, you have meters square per second square. You have landed on the same units. All right. Now, ladies and gentlemen, you are going to find a lot of questions in the now test yourself section. I will advise you to do all the exercises and send in for correction. This is what I will say on homogeneity, and then we move to other things. All right, now, ladies and gentlemen, I just want us to take a brief look at standard form. In physics, you must have ever seen people writing, let's say 3.2 times 10 to the negative 4 times 10 to the 11 or times 10 to the 23 and so on. This is what we call standard form. So now we're going to see how it is being done. As simple as it is, okay. All right. The power. Let me tell you, let me just give you the secret here. Because here people make a lot of mistakes. Here people make too much errors when trying to write numbers in standard form. You can solve accurately and you have the correct answer, but now you come and put it in the wrong form. That is how you begin to fail. So it is to the best of my interest to resolve such issue. All right, now let's look at this. When we say, if we say 3 times 10 to the power 4, it simply means 3 times 10. That's you write a 0 4 times, right? So this becomes 10,000. All right, which is 30,000. So it means this is the same as 30,000. I hope you are getting it. So what does it imply? When the zeros are behind the number, it takes a positive exponent. Now let's also look at a case like 0.000004. Now you can write this as 4.0. You now move the decimal point this way. 1, 2, 3, 4, 5, 6. So you see where it is. So it's now times 10 to the power negative 6. So mind you, when the decimal point is moved to the right, it takes a negative sign, and when the decimal point is moved to the left, it takes a positive sign. I rest my case. All right. Here now, ladies and gentlemen, I will want to talk about base units, multiples, and then there are submultiples. Just very briefly. Yes, and then we will look at one of the last thing that I will have to talk on. Yes, so all right, ladies and gentlemen, sometimes, all right, sometimes the base unit is either too long or too small. So when it is too long or too small, we now need to use something, some prefixes or suffixes. The air is not good this morning, so I got cough. Nonetheless, still have to make sure you guys are studying, so that's why I'm here. That's why I okay. Let's continue from where I was. I said you can now use prefixes or suffixes. I have arranged for you a table where you have these prefixes and suffixes summarized. Let's go right there. Here we are, ladies and gentlemen. I want you to make a copy of this table in your exercise book or whatever you are using as a notepad. Try to make it a second time without looking at it. It is going to be of great help to you. So, I'm sure you might have ever heard they will say micrometer, microfarads, nanometer, picometer, and so on. This thing troubles people a lot in how do we call it, in your exams. So I'll just this table is just making things clear. Every unit can have this prefix or suffix. So I'll give you a prefix. Okay, I'll just analyze the table. Let me not make it lengthy. I'll just analyze the table from the top. When you hear pico, it can be picometer, picogram, picoliter, or whatever. Pico, it simply means we divide by 10 to the power negative. We divide by 10 to the power 12. So if I say 3 picometer, picometer, here I mean 3 times 10 to the negative 12 meter, and life is good. Nanometer, the picometer is not always seen, but nanometer is something that you always hear about it. It's times 10 to the negative 9. Micro, if you hear about micro, times 10 to the negative 6. Milli, times 10 to the negative 3. Centi times 10 to the negative 2. And deci times 10 to the negative 1. Now, we will now say kilo. It can be kilogram, kilometer, and so on. It is now, or any units, kiloton. It can be kiloton, right? It means times 10 to the positive 3 or times 10 to the power 3. When we say mega, mega now is the opposite of a micro. So since micro is negative 6, mega is positive 6. Giga, 9, and then tera, 12. So you can draw that scale from -12 to 12. Then you name them, and life becomes good. Ladies and gentlemen, my dear aspirants, we shall now look at vectors and scalars. We will also look at vector diagrams. It is simple. If a physical quantity is not a vector quantity, then it is a scalar quantity. Then now the question that begs for an answer is what's the difference between a vector quantity and a scalar quantity? It is simple. What do you need to know? Vector quantities, they have both magnitude and direction, while scalar quantities have only magnitude but no direction. Examples are so many. For scalar, we have mass, we have volume, we have energy, just to name a few. We have distance, we have time. For vector quantity, we have force, we have velocity, we have acceleration, and so on. Now it is important to know this. When scalar quantities are added, the total is simply the arithmetic sum of the quantities. You're adding mass, 3 kg plus 5 kg plus 4 kg, just add them arithmetically, meaning that just add the number, the magnitude, right? The size, just add them. But the case is different with scalar quantities. With vector quantities. Because now when vector quantities are added, their directions are also taken into consideration. So you must take into account the size, or we call it their magnitude, and then their direction. That is why if you have a force acting due north or upward, let's say a force of 5 Newton, and a force of 3 Newton acting this way, the result will not be 5 plus 3. The resultant force would also take into consideration their direction, which will be between this. The resultant force Fr will take direction here, and as a result, the value will not be 5 plus 3. It will need to be calculated here in this scenario using Pythagoras theorem. Now, if vectors are acting in opposite direction, like this one, let's say 7 Newton and 4 Newton, the resultant vector will be on the side of the bigger one. So the resultant vector will be on this side. That is the direction. Now what about the magnitude? The magnitude will be the bigger one minus the smaller one, which will be 7 minus 4, 3 Newton. Yes, so here now you have constructing vector diagram, which I've already done so, but I'll still come back to it. I'll still come back to talk on that before we look into this, some small examples. Yeah. All right. Constructing vector diagrams. Now, there are some rules you have to follow. Okay. All right, ladies and gentlemen, Where we talk about inside a vector diagram, each vector is represented by a line. So if we're talking about force, a line like this with an arrow shows a force. Another line may be like this with another arrow shows another force. So you need to know that in a vector diagram, each vector is represented with a line. The length Alright, ladies and gentlemen, we continue from where we ended. I was talking about constructing a vector diagram. And in a vector diagram, we use arrows and direction. We use arrows we use lines and arrows. Yes. When I say line, this is a line. My pen. Okay, good. This is a line with an arrow. So the length of the line, look at these two lines. You notice the second line B is shorter than line A. It means now the magnitude, because the length of the line determines the magnitude. If this one is 7 Newton, this one could possibly be 3 Newton. Then now the arrow shows the direction. So that's why in rule 1, I say choose a suitable scale. Choose a suitable scale. Draw a line to represent the first vector. In both magnitude and direction, draw a second line starting from the tip of the first line to represent the second vector in both magnitude and direction. Now, rule 2 will say, draw a line from the beginning of the first vector to the end of the second vector. When you do this, you have completed a triangle. So if the first vector is like this, the second vector, you start from the tip, from where the first vector ends, you continue with it like that. You are drawing a vector diagram. Then now, taking into consideration its direction. So if it is going this way, if not, if it's going by that way, you also draw by that way. Now, you have to draw a line from the beginning of the first vector to the end of the last vector, second vector. So now this one now is the resultant vector. That is how you draw vector diagrams. Alright, so let's look at an example in that. An airplane, excuse me. Alright. Question reads, an airplane, this is the question here. An aeroplane is flying with a velocity relative to the air of 200 km per hour in a direction due north, like this. So you draw it. You draw it like this. You put what? 200 km per hour. Now the wind blow. There is a wind blowing from a direction of 30 degrees north of west. So 30 degrees north of west means 30 degrees from north going toward the west. So you measure with your protractor 30 degrees here. You draw again. This is 30 degrees, or you put theta, knowing that theta will be 30 degrees. Calm down. There's a problem. Need to be resolved. Alright. 30 degrees. You are not supposed to draw from here. You would rather have to draw from the tip. from here. So 30, you measure 30 degree like this. Angles are measured from the positive x-axis. So measure 30 degree from here. Okay, 30 degree should be something like this. Good. Then you put the 80 kilometer per hour there. Then the resultant should be this one from the start of the first to the end of the second. This is the resultant vector, which can be calculated. So I want to believe you get a point. This is the diagram. All right, this is the diagram here. So it's even part of the notes. So with this you can, this is how you draw a vector diagram, and you can use this vector diagram to actually calculate, to make some necessary calculation. For example, here I said draw a vector diagram to scale. Then you calculate the length of the resultant. You can calculate this side. Yes, since you know this one and this one, you can always calculate this side, because this is good. So the diagram is clearer. You know this side, you know this side, you can calculate this other side. And if you use a scale, you can just use your ruler to measure. Then now you calculate your theta. Yeah, and then they needed what? The resultant. So you calculate the resultant, which is the length r. Then now you calculate the theta, which is the direction, and you are done. Okay, dear aspirants, it is time for us to look at resolving vectors into its vertical and horizontal components. This is going to be the last part of our today's lesson. I will ask you to pay attention. So it is important to know that vectors like forces, velocities, accelerations, and so on can be resolved into their corresponding vertical and horizontal components. If you have a vector like this, let me pick my pen. All right, if you have a vector like this vector will have a component along the y-axis and another component along the x-axis. This is known as the vertical component, and this is the horizontal component of this force or of this vector. I'll call it V. So now, just as it is useful to be able to combine vectors, it is also useful to be able to resolve them or separate them to their component at right angles to each other, because the vertical and the horizontal component of each vector, my pen. All right, yeah, the vertical and the horizontal component of each vector, they are perpendicular to each other. One thing you must know. So now, if you have a vector V like this, V, you can now resolve it into, this line is supposed to be straight, so when you are drawing your own, make sure it is straight. You can resolve it into vertical and horizontal components. How does the vertical component come about? You need to find an angle, call that angle theta here. Then now you use SOHCAHTOA. We know that sine theta is opposite of a hypotenuse. Consequently, if you extrapolate this boy, the vertical component of V, you will notice that good. This is how it's going to look like. This one, this is it. This is how it's going to look like here. And now it forms what? A right angle triangle, where this is the opposite and this is the adjacent. Now you know that opposite is, you know that sine theta is opposite of a hypotenuse. So this side here, which is opposite to the theta, this side is going to be V sine theta, and then this other side will be V cos theta. I assure you, this is how to resolve vectors to their corresponding vertical and horizontal components. Example. This is what the example says. We're here. A box of weight 20 Newton lies at rest on a slope. You can see the box here on a slope, which is 30 degrees. You can see the angle 30 degrees to the horizontal. Calculate the frictional force on the box up the slope. All right, ladies and gentlemen, I also like you to know what we call free body diagram. Free body diagrams are very important in physics. Yes. So it is simply a diagram in 2 dimensions that shows all the forces acting on the body. So now you see, this is a the first thing is we draw the box. As you can see, the box here on the inclined slope at the angle of 30 degrees with the horizontal with the horizontal axis. The weight is here 20 Newton. Then the normal reaction force is acting perpendicular to the surface. That is the normal reaction force. And the frictional force is acting upward. Why? Because if this box is allowed to slide, the box will slide down. And you know, frictional force is always to oppose the motion. So it was going to be upward. I think you get. So these are the forces acting on it. Now, you have to resolve these forces to their vertical and horizontal component. Yes. The weight of the box is 20 Newton. You can see that this force, since this is the surface here, this force is vertical to the surface and this force is along the surface horizontal. So this is the only force that needs to be resolved into vertical and horizontal component. Now consequently, we have now to resolve the 20 Newton force, which is the weight, to the component along this slope and the component perpendicular to the slope. So now, when you do that, this is 20, the 20 Newton is acting downward this way like this. So the slope is this way. So meaning that this is surface. So you can now resolve it into a component like this and another component like this. Good. So now you use what I said before. You're going to have the component along here 20 sine 30 and here 20 cos 30. This component 20 cos 30. So now what does it mean? Since you are looking for the frictional force, the body is not moving, the body is standing. So it means that the force that is pulling down is equal to the force pulling up. So it means that this force 20 sine 30 is equal to the frictional force. So frictional force is 20 sine 30. You resolve that and the work is done. Like I said before, you can drop your question in the comment section. You can get to us directly and then we see how things go. This is the now test yourself section, like I told you before the beginning. Yeah, you can now test yourself. These are questions for you. You test yourself to see if you actually understood all that the teacher was saying. So this was it for the first topic in physics with I myself, Sir Godwill Yakum. Thank you for taking the lesson, and I continue to wish you good luck in your national examinations. We'll see again in the next lesson. Bye.